Spent the last 4 days talking about collisions, conservation of momentum. When two things collide with each other or something explodes into 2 or 3 pieces, then we can use this PI equals PF thing. But I don't know if you noticed, but all the collisions and explosions that we've done till now have involved one axis. Every object is either moving on the x-axis or each object in the question is moving on the y-axis. In other words, maybe something's moving north, something's moving south, or something's moving east and something's moving west, but we haven't seen any questions where something's moving north and something's moving west in the same question. That's a two-dimensional collision, or fancy word for it would be a non-collinear collision. One-dimensional is collinear, two-dimensional is non-collinear when we get east and west in the same question. But what I want you to recognize is that although they're a little bit more work, they're not really any harder. I'm going to draw a couple pictures here and ask you how I would tackle these questions, and then I want to draw the similarities between what we've done and what you're able to answer here in the next few minutes with what we're about to do, these two-dimensional collisions. So let's say I've got two objects here, object number 1 and object number 2. Object number 2 is at rest, 0 meters per second. Object number 1 is moving towards it with a velocity of 10 meters per second. They're going to stick together, and they're going to head off as one object. Okay, we've done this question before, right? Not these numbers, whatever, but we've done the question where one object is at rest, one object is moving towards it, sticks to it, and then head off as one, right? How would we analyze that question? Like, what's the technique that we'd use? We know this, right? If we're analyzing both objects, the system we'd use, PI is equal to PF. We would say M1 V1I plus, probably might as well say 0, right? You could say M2 V2I, but might as well say 0, equals M total times VF. Got it? Odds are in this question, you're going to be asked to solve for VF, so let's say VF is equal to whatever, meters per second. We don't really care about the numbers in there. Just trying to illustrate the method rather than the solution, the actual answer. Hey, nothing new there, right? Nothing new. Well, how about this one? How about if object number 1 is at rest and object number 2 is moving down this way towards it with a velocity of 15 meters per second? How do we tackle that one? Yeah, the same, right? We say PI is equal to PF. We'd say, this time it would be 0 plus M2 V2I, right? Because the first object is the one that's at rest, equals M total times VF. And then we'll probably solve for VF there. Assuming they stick together, there's only one object with a VF, right? If they don't stick together, it's no big deal. You would just say M1 V1F plus M2 V2F. Hey, nothing new. We spent 4 days doing this now, including our lab day, doing these one-dimensional, or sometimes we call them collinear collisions like this. But what about this? What if we see a question where car number 1 or ball number 1 or whatever it is moving to the right at 10 meters per second, and ball number 2 at the same time is moving downward this way to the south at 15 meters per second. They collide right here, and then they stick together. Where are they going to go if they stick together? Where are they going to go? Yes, exactly. They're going to go down this way somewhere. Don't know exactly where, right? But down and to the right. How do we know that? Well, because before the collision, there was momentum to the right. So after the collision, there's going to be momentum to the right. Before the collision, there was momentum down. So after the collision, there's going to be momentum down. So where's the wreckage going to go here? Down and right. Now, at a certain angle, I don't know what that angle is going to be yet, but that's where it's going to go roughly. How do you think you're going to analyze this? Well, we're going to break it up into components. We're going to break it up into x components and y components. The x component is going to look exactly like this. That's not what I wanted to do there. Let's just write it out again since I wasn't able to do that. The x component is going to look exactly like the first one. M1 V1I plus 0 equals M total times VF. How come there's 0 there? Object number 2 is moving now. You guys remember what x and y is, right? This is x, this is y, right? X, y. How do we put a 0 in there when clearly object number 2 is moving? Yep. Because it's not moving on the x-axis. It's only moving on the y-axis. So we'd solve for VF there, exactly the same as we would in that first problem that we did. Well, then we would analyze the y component. And the y component would look exactly like the blue one. Pi is equal to Pf. We'd say 0 plus M2 V2I equals mass total times Vf. Why is the first term 0 here? Yep. Right. Mass 1 is moving, but it's moving only on the x-axis, not on the y-axis. So it is 0 on the y-axis when we're analyzing that. Solve for Vf there. So you see how when we analyze one of these two-dimensional collisions, or explosions for that matter, we'll get to that later on, you can see how really, it's just a problem that we've done in black on the left-hand side and a problem that we've done in blue in the middle. It's just those two problems combined, right? And then, oh, wait, we have two VFs. What do we do with that? No, we can't cancel them. Somebody said cancel them. Can't do that. Enter. Yes, vector addition, good. We have an x component that looks like this. We have a y component that looks like this. And then our resultant vector will go from start to finish. And Andrew, how would you find that resultant vector there? Yeah. Pythagorean theorem, right? A squared plus b squared is equal to c squared. You also solve for that angle, and you do that using the tan function opposite over adjacent. But we'll talk about that more when we do an example with actual numbers there. Okay, let's do an example here. Example number 1. Car moving north collides with a car traveling west. Two cars entangle, head off as one. What's the velocity of the wreckage immediately after the collision? Listen, we got to write down givens in a two-dimensional problem, and we know we have a two-dimensional problem because we see north and west in the same problem. If you see north and south, that's one-dimensional. If you say east and west, that's one-dimensional. But if you see north and west, that's a two-dimensional problem. So if you're going to write down your givens, why don't we just draw it? Draw the picture. That's the best way to write down the givens here. Okay, you try to avoid drawing a picture here. You're going to make something positive and something negative, and you're going to mix up the x's and y's. Draw the picture. We're going to say car number 1 is traveling to the north. It has a mass of 1,200 kilograms and a velocity of 10 meters per second. And car number 2 is moving to the west. Okay, this is going to be car number 2 right here. It has a mass of 1,500 kilograms. And it has a velocity of 12 meters per second. They're going to collide right here, and they're probably going to go off this way somewhere, right? If we have momentum north before, we have momentum north after. Momentum west before, momentum west after. So we do our x's and y's, right? Don't ever try to do this as just 1 pi equals pf. You can't do that. It's 2 pi equals pfs for the x and for the y. Okay, let's say for pi equals pf for the x component, let's say 0, because object number 1 is moving only on the y-axis. Got that? That makes sense? Plus m2 v2I equals m total times vf. The wreckage afterwards is moving on both axes, but it's got an x component, so we have to include that. So we say 1500 times negative 12, because it's to the left, equals 2700 times VF. And VF will equal, when we say 1500 times negative 12 divided by 2700, negative 6.6667 meters per second. Well, then we got to do the y component. For the y component, we say m1 v1I, because object number 1 is moving on the y-axis, right? Plus what? How much of that 12 meters per second is on the y-axis? 0. So we're going to say plus 0. It's equal to m total times vf. This time it's 1200 times 10, 2700 times VF. When we do that, we get 4.44. That's really nothing different than what we've done for the last 4 days, right? Except it's twice the work, because it's 2 problems. When you're analyzing x, pretend y doesn't exist. Anything on y-axis isn't there. When you're doing y, pretend everything on the x-axis doesn't exist. Now what? This is really 3 problems in 1, right? 2 physics 30 problems and 1 physics 20 problem. Andrew, what's the physics 20 problem we got to do now? Yeah, like the vector analysis part, right? Let's draw this out, though. We have the x component that is 6.667. How did I know to make that left? How did I know that 6.667 vector is to the left? It's negative, right? 4.44 is positive. It's positive, so it's up. You guys learned in physics 20 that you always draw vectors head to tail, right? So you never draw it like this. Okay, you got to draw head to tail, not tail to tail. A resultant vector is right here. So I'm going to say V is 6 points. We don't need to put in the negative now when we're squaring it. A squared plus B squared is equal to C squared. Let's do this one on the calculator together here. Let's say 6.6667 squared plus 4.44. Let's square root that. 8.01 or just 8.0. And theta is the inverse tan function of opposite over adjacent. Do that one as well. Make sure you're in degree mode on your calculator. Okay, I'm in degree mode. You can see there. If you're not, then make sure you put it in degree mode. The inverse tan of 4.44 divided by 6.6667, 34 degrees. I'm going to say, what is that? 34 degrees. What of what? Something of, I'm going west and I'm going north. Is it west of north or north of west? What is it, McKinnon? North of west, yeah. have to include a direction because velocity is a vector, right? North of west is opposed to north of west, or as opposed to west of north, because you look at it, I'm measuring my angle from the west, right? I'm not measuring, this would be from the north. I'm measuring it from the west. So I'm measuring it north from west. Because it goes north, but measured from the west. North from west, or we'll just replace the word from with of. North from west, or north of west.